Is NextFlex sponsored AI for Hybrid Electronics webinar. Our title is Harnessing the Power of AI in FHE Design, Understanding Challenges and Unlocking Opportunities. As I think most of you know, NextFlex has been for the past year looking at key opportunities in hybrid electronics, working with our industry and academic membership, as well as our US government partners to identify what are these opportunities for AI to impact the field of hybrid electronics broadly, from manufacturing to design to implementation and manufacturing operations. We've seen a number of different opportunities, things like boosting design and manufacturing efficiency, improving product reliability and yield, enabling smart adaptive devices, leveling the playing field for small manufacturers to compete with large manufacturers and really lowering the technical barrier, and strengthening US manufacturing and industrial-based resilience. NextFlex is working on developing an AI for hybrid electronics roadmap, working with both members and non-members to put together this roadmap that really lays out what are the opportunities in the field across all of the different opportunity areas. The purpose of this roadmap is to align the ecosystem for hybrid electronics and electronics more broadly around these shared opportunities and priorities. It allows us to guide our investments, the investments that we make in projects that we fund to advance the field. It allows us to identify actionable and high impact opportunities across the value chain. And it also allows us to support education and workforce development opportunities, such as de-risking AI adoption for small manufacturers, improving technician training, and enabling our workforce for what's already here and what's to come. You can see that we put a lot of thought into what the structure and framework for this roadmap will be. And we're looking for volunteers to help us construct this, put their ideas into the roadmap, make sure that we're capturing the current state of the art, the things that you do today, the things that you will do in the future, and the things you'd like to be able to do in the future. To support this activity, this road mapping activity, one of the things we're doing is running this AI for Hybrid Electronics webinar series. And so I'm glad that you're here with us today. The webinar series is open to both NextFlex members and non-members. And since we do have non-members in our audience, I wanted to just briefly touch on who is NextFlex in case you're not familiar with us. Well, NextFlex is a manufacturing innovation institute whose mission is to create a strong US industrial base for hybrid electronics manufacturing. We do this through three focus areas that we call pillars. The first is advancing technology and manufacturing. These are the technologies and the manufacturing technologies that are required to design, to build, and to implement hybrid electronics and integrate them into systems. The second pillar is establishing and growing the US manufacturing ecosystem, ensuring that we have suppliers and providers at all the different parts of the supply chain, from the software for design to materials to contract manufacturers to OEMs, equipment manufacturers, all the different parts in between those to enable the US to compete with the rest of the world in the area of hybrid electronics design and manufacturing. And finally, the third pillar is securing human capital. That's our education and workforce development mission. We can have the greatest technology and manufacturing ecosystem, but if we don't have the people who are actually going to do the design and manufacturing work, then we won't be able to compete. So it's absolutely vital that we have that as well. We do that through a lot of different activities. We have our consortium with more than 200 industry, academic, and government organizational members. We have our technical working groups, 11 technical working groups focused on hybrid electronics, areas of hybrid electronics. We fund projects that we call project calls, more than $145 million over the last 10 years. We provide information dissemination, workshops, webinars such as this one, in-person and virtual events. Our members have access to our member portal with project information, with lots of data, event archives. We have our education and workforce development activities where we've impacted more than 27,000 participants, students, and industry professionals alike in more than 12 states. And then we have our technology hub. We're not just an organization that coordinates this field, but we're also actively participating in it. We have the ability to do everything from initial manufacturing evaluations to prototype development, design and development, to low rate initial production. Most importantly, to transition all of that out into the industry. So if you're interested in those things and you're not a NextFlex member, you should contact us. Lastly, I'd like to announce some upcoming events to raise awareness here. For NextFlex members, this is exclusive to NextFlex members, our upcoming project webinars. You can see in the list here, webinars for the rest of the month of December. We have 3 more, and then for the first half of January, we have the next 3 listed. I believe we have 4 scheduled for the second half of January, and I thought that was just too many to put on this slide. If you're a NextFlex member and you're not receiving the invitations to these webinars and you're interested and would like to, please contact Eliana Schoenberg at her email address is on screen. I think many of you know her. Next up, also exclusively for our NextFlex members, are the next part of our technical working group road mapping sessions will be starting in January. The 11 technical working groups will each be meeting, as well as cross-technical working group meetings focused on a number of areas that are listed on the screen. And I do want to highlight specifically that those cross-TWG opportunities, as well as those cross-TWG meetings will consider things like alignment to the DoD's critical technology areas. So if hopefully you're part of the technical working groups already. If you're not, you can contact Nick Morris to join those for NextFlex members. Oops. Last announcement of an upcoming event, and this is open to all. NextFlex Innovation Days will return June 9th to 11th in Mountain View, California. This year, we're going to be holding this annual member meeting in conjunction with the TechBlock organization and their Future of Electronics Reshaped conference. Working together is really a great opportunity for us to strengthen the industry, to benefit our member community and the broader community as well. So please join us for things like high-profile keynotes from DoD industry and EWD experts, as well as technical presentations, several member-only activities, and lots of networking. So hope to see you all there. And finally, it's my pleasure to introduce our speaker today. David Wiens is product manager at Siemens, responsible for the areas of EDA, the EDA industry. Over the past 40 years, he's held various engineering, marketing, and management positions within the EDA industry. David is one of the key champions for Siemens and frankly the EDA area within NextFlex, and so we're really pleased to have him presenting today. He'll be sharing with us about harnessing the power of AI in FHE design. David, I'll hand over to you.
Right. Looks like I'm sharing the right screen. Let's go ahead and get going. All right. Yeah. Thanks, Scott. Yeah, as Scott said, I'm within the I'm within the EDA space. Siemens is a large company. Siemens, overall has a huge investment in AI. Over, I don't know, 1,000 AI scientists hanging out all over the place. Just made a commitment to over $1 billion in new investment in AI, and notably opened up access to all of the electronics designs that happen within Siemens to us to train models on. And as I'll talk about, that's one of the large challenges in the AI front. I'm going to be talking about FHE. Some of the examples will look like the PCB close cousin, and that's okay. There's a lot of similarities in the design of FHE and PCB, as long as it's planar. I'll also note some of the non-planar potential for AI as we go through this. Spoiler alert, AI is not close to replacing humans in electronic systems design. There's potential, but it's still a ways off. The focus, therefore, is mostly on augmenting engineers rather than replacing them. And lastly, I should note, this pitch is not intended as a product pitch. It's, as I say, I'm talking about challenges and opportunities. I've got one slide talking about our AI. So if you want to know more about what we're doing in AI, particular solutions, contact me and we can do that offline. So let's go ahead and get rolling. I'll talk first of all about the promise of AI. Talk about the reality where we see it today, plausible areas, use cases of deployment within the design process, and finish off with challenges in that deployment, issues people are seeing with AI. So just to start off, I mean, it's obviously a hot topic. AI is everywhere, and there's plenty of discussion about replacing humans. It's heavily on the software side, but other areas as well. Hardware still doesn't have the same projections of replacement, but just the same, engineering teams everywhere want to know how they can optimize their resources, and that often looks like reduction in headcount. Again, we're still a ways out of that, and what we see is an opportunity for optimizing the productivity of engineers rather than replacing them. So within that context, what's the promise? What we see, particularly at the high end of design complexity, we're really pushing the envelope in terms of signal speeds, protocols, densities, multi-board system complexity. All of these are pushing the envelope on design complexity. Along with that, we see a retiring workforce that's not being matched with the incoming new hires coming out of the universities. So there's a limit to the human resources, but also potentially to the compute resources that are necessary. You couple that with schedule pressure, design and product cost pressure, and what we see is this gap being developed between the needs and the capacity, internally to deliver on that. So the promise is closing that gap, bridging the resource gap, trying to find ways for AI to improve the productivity of the engineers that are in place, to make up for the absence of retirees and not enough new hires, to accelerate time to the product, enhance the productivity of both individuals and teams, and finally to enable optimization of the product. It's not just about getting it out faster; it's about optimizing it for multivariable situations, and I'll talk about some of those as we go through this presentation. So, I have to offer a word of caution before I get going talking about AI. AI it's the newer tool in the arsenal. It's not brand new. I got to say, you see my gray hair. I studied artificial intelligence in college. Back then, it was a lot different than it is now, but it's been around for a while. The hype curve around AI, is largely a result of the GPTs that have come out just in the last few years, and that move into generative, and then into agentic. That's what's caused the largest interest level to spike. But AI has been around for a while. But AI is just one of the many tools in the tool chain. For instance, if you're looking at, in this case, trying to accelerate design cycle time, AI can play a part. But basic automation. I should have put my chat on another screen. But automation comes into play in multiple forms, and as does integration between tools, trying to optimize the flow. Digital twin verification, trying to do verification during the design process, not after. Design reuse, multi-domain co-design, concurrent design. These are all what I'll call best practices that are widely available across most tools in the industry. What I'd recommend then is just leveraging the existing best practices. Take a look. When you're looking for solutions, AI has got to be one of the predominant topics that I get pulled into conversations with customers now. Everybody wants to know. It's the same thing within Siemens. We're being asked to find new and innovative ways to use AI in our everyday jobs. It's a real thing, but at the same time, we need to make sure that the focus is really on the solutions to problems and not how the solutions are created. In other words, going back to the root cause, what are we trying to solve, not just how can we screw in AI everywhere possible. In the world of engineering, to me, it's the equivalent of software engineering anyway. It's the equivalent of specifying, that you want that solution, created in a C++ or some scripting language, basically, dictating the approach as opposed to dictating, what you want the solution to do. So let's focus on the solutions. But hey, I'm here to talk about AI, so that's what I'm going to talk about. But I'll also note, not everything needs AI. And this just kind of follows on a bit from the previous point. But today, here's an example. Every design has to have components, right? You're putting components on a circuit. You need a component library. Where does that library come from? Well, you've got multiple component vendors. So this is just a sample set, not all of them, of course. And they supply limited information. You can get some of it online. You got to wonder about, do you trust that? But you get a lot of it from the vendors themselves. It often comes in the form of PDFs. Sometimes it comes in the form of models. But again, you have to trust, trust those sources. So this is the world that exists right now. In comes AI. And this is a heavy area of AI. It's frankly a fairly simple one. Using AI to crawl PDFs, and even we have deployed solutions to do just that. But functionally, you got to look at this and say, okay, the component vendors are creating derivative content in the form of a PDF. We all know that's error prone. We've seen it enough times. And because you're translating data multiple times, that also introduces the potential for errors. It also doesn't have all of the information necessary. For instance, most data sheets don't have things like simulation models for signal integrity, power integrity, thermal, other things in them. You got to go find that from another source. So this is, this AI applied here is a solution. I won't say it's not a viable solution, but I got to say there's an alternative in this case, which is a JEDEC standard that's been developed, with partnership across the industry, that represents, the closest thing we can see to a complete digital twin model, meaning it's got all of the data that you need in it. What it needs to drive the adoption of that is an ecosystem. The vendors supporting it on on their side, and the tools supporting it by pulling it in, reading it into their tools. So that's, it's not complete by any means, but it's a non-AI solution, and it's quite, I would say it's a better alternative to the AI approach, if in fact it gets deployed across the industry. So I guess that's a shameless plug for the standard, but also noting that there are, as we say, multiple ways to skin the cat. Just talking about the state of AI in the industry. There's a lot of startups out there. There's a lot of AI being shown. This is just to kind of set the landscape for what I'm going to talk about, some of the issues that you might see if you start looking at deployment. On the left, you see a manual design. This it would have taken a few days to complete. We can assume it's at 100%. That design was then thrown into an AI router. Just a router, not placement. So the placement you see is identical. And in this case, the routing was canceled after 5 hours. You say, well, 5 hours is better than days, certainly. But it was canceled after producing multiple iterations and never getting past 59%. So you look at that, and by the way, yeah, you look at that route, you go, not exactly meeting my timing requirements for starters. That's one of the limitations of AI today. There's a lot of, obviously a lot of design constraints that go into a design. And if all that's fed to the AI is a resulting design, you're losing a lot of the IP that went into it. You're losing the constraints, for instance, the performance constraints for, say, timing, these differential pairs, coupling, for manufacturability. All those constraints are absent from the end result. In addition, the process, how was it created? What steps were used? That's also critical to optimizing a design. And if you're just looking again at the end result, you're missing all of that. So those sorts of things come into play in what we call fine tuning. And you can, in fact, as a human in the loop, bound those parameters to some degree, those features, when you're doing feature engineering, to optimize it. But by and large, what we see is a lot of folks throwing designs at AI without that kind of feature engineering. So then on the third case, we took a router, happens to be our router, and we threw it at the design, and you see, wow, look at that, 11 seconds. Now it ended up at 98 seconds, and this, by the way, or 98% rather. this, by the way, has been the the death knell of auto routers for decades, literally. That, well, you got to close, but that 2% is near impossible. Thanks, but no thanks. In this case, we looked at it and said, hey, that last 2% would have been an easy close, so that's not really relevant. But you also see another instructional element here, which is that really doesn't look very good, now does it? It's not coupled very well. In this case, there was also training required. In this case, the engineer that was doing the auto route had never done it before, didn't know how to set up the router. So in addition to setting up design constraints for performance, for manufacturability, you've got to set up constraints for the router so it knows what to do on the design. And in this case, that wasn't done, so you see a natural result from that. So again, this is non-optimal. But it does showcase, again, the value of training, but also the potential for AI to get into the equation and optimize some of that setup time to ultimately produce a result. In the end, what engineers care about is throughput. So if it takes longer to set something up and run it and then clean up afterwards than it does to do it manually, they're going to stick with manual quite naturally. Same thing is true of algorithmic automation as with AI automation. So just looking at a few types of AI that are out there. These are common terms. You probably heard them before. The world of predictive and machine learning has been out there for a while. Here where it takes existing historical data, makes predictions, and continues to learn from the data to optimize over time, trying to find patterns in designs. And I'll showcase a few examples of this later. The big area, as I noted, is that's currently hot is generative design. And in this case, it's taking that new content and the training data and generating what's viewed, the term generative. It's generating new content, but really it's derivative content, right? It can't do anything that it wasn't trained on. But it learns existing patterns and structures. It's really good at text, images, also image, pattern recognition, things like that. A close cousin of that is natural language processing, and this, of course, is a part of generative design, using that both text and voice to enable a change in the user interface between software tools and humans. The combination of natural language processing and generative is one of the fastest developing areas within, I can tell, within the products of electronics design, because frankly it's an easy plug-in to take something as simple as changing the way you're not going to, if you're sitting there doing a layout in a design, you're not going to use voice direction to say, hey, please move over here, now move over here. That'd just be frustrating, painful. A mouse is still much better at that, but you can tell it, please execute this command, or can you give me the directions on the steps that I need to do to execute this step, to this larger step, and then, oh, by the way, can you just execute it? Can you do it for me? These are things that are natural plugins to existing software in all wide variants, and you can expect to see them in most electronics design tools, in the next few years. Reinforcement learning is out there. It's less used. It requires tons of data, and in some cases requires a human in the loop to do the reinforcement. Some of that reinforcement can be done, of course, by the AI itself, but it takes a long time, lots of data. And then the last, really the newest hot topic is agentic. Agentic is more of a process tool than these others, and it really leverages all of the others. We see great potential in the agentic space, just because it has the opportunity not again to replace engineers as agents, but to replace the way in which they engage with the tools. Just like the hype curve of generative AI has spiked, now so is the curve on agentic AI, and you'll see simple things like Like I was talking about the simple use case of perusing documentation for a product using natural language processing. Some people now call that agentic AI. So there you go. Agentic's now going to be the new generative. But just to be clear, agentic is much broader than just that use case. So one of the things to look at when you're talking about AI is that scaling from a simple prototype into production. And of course, in electronics design, this is a natural part of your process. You understand, what a prototype is worth and what something that's ready for volume production is worth. In terms of electronics, the same thing is true in software. And one of the amazing things about AI applications, particularly with a lot of open source software available, easy plugins to AI engines, is that you can create a prototype almost overnight in some cases. We've got inside our group, we've got hackathons. We just finished one last week, and this is where our software engineers get to go out there and try something they weren't asked to do, right? They have an idea, they want to create something new. I think, I don't know, 70 to 80% of the ones this time were based on AI implementations. It's a lot of interest in it internally as well, right? Those sorts of things create, just in a day or two, can create very simple prototypes. That's the stuff up here. What it takes to harden it is much harder. You've got to start defining, what does accurate look like? We know a lot of the potential for AI is, part of the issues are the incorrect answers that it gives along with the correct ones. And so you have to have a human in the loop, or you have to have some other way of doing that accuracy testing. Again, if it takes longer for the human in the loop to do the verification than to do it manually, you have a lost cause. Then you've got to figure out how to start scaling that, make it work dynamically and automatically within the flow. And then finally, look at all those corner cases. It's got to be, as an engineering solution, you can't have a, hey, it works sometimes, you might want to try it kind of answer. And you need to know, what it's going to produce as close to, a deterministic process as possible that we've been used to dealing with algorithmic solutions for years. If you push the button twice and you get different answers twice, you're probably not going to enjoy that, right? You want to know every time you use a tool, it's going to give you the same answers. So the caution here is that, when you start hearing about it, AI implementations, when you start seeing the press releases, they're coming out right here. That's way early in the process. And so, as you look at AI solutions, and I'll finish this presentation, with some of the questions that you should be asking. You should be asking us, as vendors, Siemens, and you should be asking everybody else is, what some of the things that relate to, can I trust this? How many different use cases does it work with? So that scaling is a difficult process as we move through this. So let's talk about some of the reasons why it's difficult. First off, model training, right? There's tons of effort. You hear about the billions that are being spent by folks like Google, OpenAI, Anthropic, all these guys, both on model training, of course, and on infrastructure in terms of huge data centers to support people using those models. That's fantastic. Frankly, there's a lot written about how it's not sustainable, but at some point, quantum computing will hopefully come in and help some of that. But what that's doing is, for the cases that LLMs can help solve, that's solving the model training issue for us, right? We don't have to go out there and train our own models. We can leverage those. Certainly, we have to develop trust in those, and we have to wonder why there's so many and which ones to use. But a lot of that training is happening already. But in the case of design tools, that creating the models either by fine-tuning LLMs or by creating non-LLM models, is quite difficult. That digital twin model complexity is rather severe. It's multiple domains. It's electronic and mechanical for starters. You don't have an electronics product that's not both of those ever, right? It can involve software. It can be multidiscipline in that there's a physical incarnation. There's a signal integrity element to it, power integrity, always, manufacturability, cost, all these disciplines have to be considered. And there's a lot of variance in terms of design types. Training a model to do power supply probably isn't going to help you much when you want to do your high-speed digital. Training a model likewise on a design that looks like this probably isn't going to help you much to do a design like this. So that variability of models is a huge limiting function in terms of how you can ultimately train those models. There's obviously the more data you can get that you can drive through the training engines, the better, so the usefulness increases. And where real design data and process data doesn't exist, then there's a new world of synthetic models that are artificially created, ROM, which are reduced order of magnitude models, surrogate models. There's tons of different ways that are being evaluated that try to work around that heavy model training problem. There's also a question of learning on the fly, AI versus training up front. If I can, for instance, start working on a design today and have basically an apprentice AI sitting over my shoulder, well, that's no impact to me. It's just learning as I go. That's frankly, that's acceptable. But if I have to, and then eventually it increases in value as it's learned more and more. But if instead I have to, take time out and go do a whole bunch of training up front, that's an extra resource that probably didn't have in the engineering organization to go do that and take the time to do that training, if in fact I even have all of that data necessary to do it. There's really the last thing to bring up here is, where's the data coming from? All of us are invested in trying to produce solutions, us vendors that are out of the box. We're trying to minimize that model training as much as possible. And one of the ways we can do that is by, at a minimum, defining the criteria that should be trained. In other words, don't let loose, a AI on a whole bunch of designs and force it to figure out what's important in that design. Do that feature engineering up front so that when the users take it on and apply it to designs, it's much faster. But so the question is, does that model come trained out of the box from the vendor? Does it work on user data, which is the most likely case, or is it trained from open source data, which I guess is another form of user data? But of course, in the world of open source, you got to question: is this at all accurate? And can I really trust it? One of the issues with user data, of course, if that's the way this path goes, is that the size of the company and the number of designs that you've pushed through over the years is a limiting function. Startups are going to be handicapped in this process if user data is the primary criteria for model training. That noted, a company that's been doing designs for 30 years needs to understand that, a design from 30 years ago probably isn't good at training designs for today. In other words, if 30 years ago I was doing, 10 and 10 spacing, trying to train it to do 2 and 2 for today's designs probably isn't a good idea. Next up is IP security. And in this case, the first question is, what is IP? Naturally, we all think about the design data, that final design, right? But as I noted earlier, how you did the design, in other words, the process, and the constraints you use are all critical parts of your design process, of the IP that goes into it. And so you have to think about all of that as intellectual property, and would you want any of that stuff, let out to others? So can things like that process data that helps with decision making parameters, can that be anonymized, federated in a way that extracts the IP out and isn't exposed to others, or is that part of the IP itself? That's an open conversation, and frankly, it's handicapped some of the discussions around using large data sources from multiple companies. Even if the IP can be protected by some neutral source, who really knows what's being pulled from that, and is some of the IP still being taken out? And if not, is synthetic data good enough instead of true design data? There's of course permissions required to extract models from IP. Obviously we see that in all the lawsuits against OpenAI and others around how they actually got the data to train their models, and whether in fact they had permissions for that. I can tell you, as a company like Siemens, IP protection is a serious issue. We get tons and tons of user designs through our doors all the time, with engineering teams, looking for help with a bug or with some design techniques, consulting, all kinds of things. We cannot use a single one of those to train models, not one, because they are customer IP, not our IP. Now we can ask for permission, and that's, in some cases you can find people that'll do that, but generally that's not, that's an easy no for companies. They don't know what they get out of it, therefore they're not willing to give you the permission for it. And of course, infringement. If you don't know where the models came from, you don't know necessarily if IP was infringed in the process, and then you become party to the next lawsuit that comes out about that infringement. Cloud is a natural fear associated with IP security. It existed obviously before AI, and it continues today. And so trying to figure out how do we get through this if the majority of AI engines live in the cloud because of the scalability of compute resources? How can we get around that? And I can tell you, we've worked on solutions to this. We have both cloud-based solutions as well as on-prem solutions. But if you bring it on-prem, you got to know that that's a compute resource you're looking at, right? That's cost naturally in terms of that compute, and as well as to some degree, disk space for the models and for your design data as well. It's not, the disk isn't nearly the critical issue. It's more the compute power that's necessary if you want to bring it on-prem. And so from a model management perspective, you've got to look at it. It is going to be one of, management of models and management of the design data necessary to train the models is going to become a huge, growth area, a huge challenge for everybody, because you've got to wonder, okay, is that model limited to just a user? Can it be used across a design? Do I, within my company, have, say, security restrictions? Like I've got ITAR designs over here, and broad consumer designs over here. I can't cross paths on those models. All of those sorts of variables have to be considered in the models that you're using. You can't just throw everything you got at it and see what happens. All these examples I've got over here on the right, I clipped out of all the T's and C's of various AI vendors, and so you can see this isn't the normal stuff that we talk about. This is all lots of IP stuff that they're having to put out there to reassure customers that their IP is secure in the process. And of course, that's up to you to trust that. Third is verification. In the case of things like a chat GPT, any of the GPTs, you're the human in the loop. You get to look at the results and you get to determine if they're accurate. Some of that just is a matter of the eye test. Yeah, I don't believe that. But a lot of it, there's plenty of things. I get chuckles out of prompting GPTs just to see how wrong it'll. These GPTs are functionally sycophantic, right? They want to please you, and so they'll give you wrong answers every day if you ask for them. And so you gotta, that's a, that's a garbage in, garbage out kind of thing. If the models weren't trained accurately, the results aren't going to be accurate. But you then have to wonder, okay, what kind of testing needs to be applied to this? And as I mentioned earlier, you don't necessarily want to be, relying on human in the loop to do that verification because of the time that it takes. And so you want to figure out, okay, how can I test this through normal means, like say a DFM rule checker. Everybody does that. They should be doing that. How can I employ that DFM rule checker to look at the design to ensure that what was created is manufacturable given the constraints that I'm dealing with today? How can I, maybe run it through a simulator or an electrical rule checker? These are all tools that exist out there. This is the place where they get to be deployed in a way that's not, ideally not human in the loop. Basically, get the AI, perhaps with an agent involved, to produce a design element and then do the checking itself to verify that it's accurate. Of course, the question is, how will those, how's that testing going to be done, and when does testing stop? When do you trust it? Anything with automation today. For instance, pretty much everybody runs a automatic design rule check, right? That's a fairly typical thing. You've done it on dozens and dozens of designs. You start to trust that what it's going to give as results is accurate. Same thing on manufacturing outputs. Most folks now will trust the automation. They may not trust themselves, and that they created different variants from different versions of a design that go out in one package or something like that. But by and large, the automation is trusted. So you can stop testing it, proving that it works. With AI, when does that stop, if ever? And things, again, with AI, we know it hallucinates. We know it might use old data. It might plagiarize. How do we know that? Some of the variability, I was noting earlier that, you push the button twice, you might get different results. This was a comment, I was asking Gemini about this, and it actually said, that's a feature, not a bug, to be variable. That might work when you're asking it for a paragraph of text. That's not true in design and engineering, right? You want accurate results. You want deterministic results. And then lots of other things, data sources, where are they coming from? And so ultimately, you end up with this thing called industrial grade AI. And I'll get to this at, I think on my last slide, trying to spell out what industrial grade really means to optimize design. I'm looking at the time, and I'm going to accelerate through some of the rest of this, but just finishing off on the last, challenge is really related to adoption resistance. And this, I can say, I've been around for a while, I can say pretty much every form of adoption incurs some resistance. Some of that's, it's all very natural. Some of it's based on the results just don't match, what the human can do. Some of it, of course, is based on a fear of replacement. That's been, automation since time immemorial. But certainly there's resistance to AI, which is largely well-founded, right? Is it really going to help me? Is it going to create more problems than solutions? But it's a human element that has to be considered in this process. Functionally, you've got to show value to the engineers. What's the net result, and how is that value defined? There's plenty of AI fatigue that's coming out now. People have seen lots and lots about AI, and so it's like, oh, really? Just you put AI there, and that's there's a new term called AI washing that's out there, where basically everybody's saying, oh yeah, I got AI inside, just trust me. Just because they want the buzz of AI. Some instances where there've been proven to be humans in the background instead of AI, just trying to get that buzz out of the term. And then the last, and it's legitimate, resistance is because of the potential for cost, right? Do I have to, if I want on-prem, what's the cost associated with that for compute resources, time associated with that? And I've got to point out, in terms of tool usage, what we're looking at, particularly with cloud-based LLMs, is a switch over to consumption models for pricing. That means the more you use it, the more you pay for it. And that, when you have, fixed capital expense budgets, that's a variable that you may not want to consider. So got lots of types of AI where that could be used in the design process. I've got just a boatload of different use cases. These are all use cases that I've seen people working on. I won't say this is all the use cases I've seen where people have created functional solutions. But what it represents is a lot of experimentation with AI in the design process. Some of it's related to specific tasks like the stuff up here. Some of it's related to more general things like that product support thing. That's just a core infrastructure element, process predictions, core element, script generation. And these, frankly, are all based on LLMs and are going to see a lot faster development than most of these up here. You can look to see most of these in products quicker than these. But when it comes to real productivity, some of the opposite may be true, that the real productivity is hanging out up here. Design agents are down in this space, more of the general type tool. That is a big potential for improvement. Specific to FHE, what we see in that space is a process that looks very similar to the PCB world. All these steps, you can look at that and say that's PCB, but there's a lot of differences that happen. There's a lot tighter ties between electronics and mechanical because these devices are either flexible or conformal. There are potentials in this space if the world of additive manufacturing can kick in and support things that are non-planar that look like this. That's where AI can enable more of a true 3D electromechanical structure definition. I also see potential in material selection and in manufacturability verification. There was discussion about the manufacturing side last week, so I'll skip some of that in the interest of time. Agentic, this is pipe dream vision, but the world we're looking at is moving to agentic. Of course, for agents to work, the underlying functions that they're interacting with have to work. And so there's lots of AI beyond just that human interface changing with an agent. There's a lot of other things that have to be built into that to make it work. But this process in which you have a bunch of agents, functional agents and orchestration agents being applied to design is where we're headed. This is just a few of the examples, and again, we want to leave time for questions. So I'm going to move off of this, just saying this is what we've got within the Siemens portfolio for AI to date. We got lots of roadmap beyond that. I'd be glad to talk to anybody offline about some of these use cases, or even our roadmap. Just contact me offline. Just to showcase, though, in conclusion, what we're looking at with AI is something that's really production grade, right? Production grade means it's accurate. It's accurate all the time. Means there's a way of verifying that it's accurate. Means that it's usable. It's easier to use it to adopt an AI tool than it is, and the results are faster than if you've done it manually. It's general purpose. It works across a wide range of conditions, and it's robust. It even considers all of those corners in designs that come out. So all of that, all of those are conditions for production grade. And then I've just got questions, questions that you should be asking as you consider AI in your engineering processes. Anybody that's doing design today is looking at AI just because if nothing else, their management's asking them to. But these are some of the critical questions you've got to ask. Does it consume my IP? If yes, does it share my IP, or is it somehow walled off from the rest of the world? Does it operate in the cloud or on-prem? How much training does it need before it's productive for me? What are the hardware requirements? Do I need more hardware, on-prem, or is it all in the cloud? What's the cost model? What am I looking at when I really deploy this thing? And then lastly, how do I validate it? What's my approach going to be to ensure that what I'm getting is really not garbage? So with that, I'm going to end and see if we got questions. Scott, do we have any questions coming in here?
All right, David, thanks. That was a fantastic webinar. Thank you very much for the presentation. So for the audience, we've got several ways to ask your questions. You can raise your hand and we'll try to unmute you to let you ask the question yourself. There's also the question pane. You can enter the questions directly into that and I'll read them off for you. I don't see any right now, but I've got one, David, that I'd like to ask. And that
Sure.
addresses this question of training. You talked about it, for a good amount of time, but when I think about something like frontier large language models, right? They're essentially trained against the entirety of everything that humans have ever written, right? Looking at the entire internet, everything that's available there. Mm-hmm. That is massively more than even if we had access to every electronic design that was ever made.
Right. Yeah.
Even if we didn't have the IP concerns and limitations that you talked about, what do you think the implication of that is for the rate at which, say, design tools or even just checking tools are going to be able to advance relative to the really rapid pace of improvement that we've seen in LLMs over the last couple of years? And does that push us into a realm, maybe I'll anticipate the answer, does that push us into a realm where we really need to, I'll say, resign ourselves to the idea of synthetic data? And what might that, say about the prospects?
So, it's well, okay. So the LLMs were turned loose, right, on the world of data, and left to figure out, every last thing about, the English language and every other language that they're applied to, and without really any feature engineering. Meaning, it's like, okay, I see a sentence, and I see enough sentences, I start to learn the, not only the words of the English language, but in what order they should be correctly utilized. And same thing for every other language. And so in that process, without feature engineering, if you have tons and tons of horsepower, you can solve the problem. In our world, without all of that horsepower and without definitely not all that data, you're left to trying to simplify it with feature engineering, which means human in the loop saying, hey, that this characteristic is more important than this characteristic in a design. How close these two parts are apart from each other is important, but these two parts it's not. And for instance, decoupling capacitors next to a BGA. Okay, that's really important. But the proximity of the is of the edge connector. How important is that relative to to say a resistor? Well, short of manufacturability, perhaps it's not. So there's a difference in the value of the things that just something looking at a pure layout of a design, if that's the training data, without, by the way, is it trained on the schematic too? Is it just the layout? Is that really, you start to think about the world of reverse engineering. I mean, this is what AI is doing, right? It's reverse engineering design. So to understand the potential to, not understand what it did, but to recreate that. And there's lots and lots of data that's, that was needed in addition to that layout to create that. So feature engineering is one of the aspects. Synthetic models can come into play. I mean, synthetics are things like, okay, I've got a design with 5 and 5, lines and spaces. I can artificially, create one with 4 and 4. Is that helpful? 3 and 3. That's synthetic data. Or surrogate models, which really, says, okay, I've simulated this condition and this condition. Surrogates are creating models in between those bounds that I have. These are all ways to accelerate that training, and frankly, to find answers quicker when you're actually doing, leveraging AI for simulations. It's not just in the training. But what I think it's going to limit, one of the things AI is just really not very good at is understanding all those characteristics in physical space. It's great at text-based things, voice. Those are things where it's great at, just largely because of the data it's been given. But understanding physical criteria is one of its weak points. And so instead of just trying to brute force, train it the same way, LLMs have been trained, we've got to look around that and try to break it down into smaller problems. Say, hey, look, can we solve problems on, how to optimize the grouping of components that come in from the schematic to the layout? Is there something we can do there that we can learn from? Can we learn particularly maybe about diff pairs? How can we scale the problem down to something that's less than that big bang? Hey, I push a button and I get a result. Because honestly, you go out there and you will find solutions largely from startups that say just that: give me requirements and I'll give you manufacturing outputs. And what they've done is they've shortcutted that whole training process, right? They don't have generally access to all the designs in the world. If you will just ship your design to the cloud, they'd be glad to use that as part of their training. But then the question is, does that training help others as well? Are my competitors going to be enabled by the training that I give it based on my design? So there's a lot of promise with this, but I'd look for more of those incremental improvements to come out, and maybe we can break it down into small enough incremental improvements that it starts to look like broad automation. But again, that's something that's measured in years at this point. I'd say easily a 10-year span.
Yeah, you make a good point that one of the big differences here is that when you assess the English language, you look at a book. How do you interpret what the author's intent was? What were they trying to say versus what did they actually say? Where in the electronics design, we have documentation, whether it's made available or not, about what was the goal. We've got to your point, the schematic in addition to a layout. We have all the requirements and the specifications for the components that are being incorporated in it. So if we incorporate all of that, we actually have much more connected data than we do just in the case of predicting what words or what are come next in a series.
But that's just a wild additional level of IP that's going out there, right?
Sure is.
And again, everybody's really, really itchy about just layout data.
And for good reason.
I can tell you, we've run a design competition for years, and all we need is layout data. We don't need the schematics. Oh man, that's just that's a nightmare to get. If you ask legal, they're going to tell you no. Naturally, they're going to tell you no, right? And so here the question, it's always a risk versus reward thing. Okay. If we, in this case, design competition's easy. It's okay. As a company, I don't get anything out of that. It's more an engineering reward. Nope, big nope. In the case of AI, okay, if we unleash all our designs to help train models, what's the reward? Is that is the risk justified in that equation? That's going to be asked over and over again. To as these solutions come online, either that or everything's going to have to go on-prem. And then it's a question of how do I validate it and all the other points I raised. But that IP issue, as long as data is leaving the factory, there's going to be the engineering team, it's going to be a concern.
Sure is. All right, we've got about 2 minutes left. Last call for questions. See a hand or no? All right, David, I'm going to say thank you very much. Really appreciate this. The presentation has been recorded. If anybody wants to forward it to colleagues, it'll be posted on the NextFlex website fairly soon here. All right, David, thank you again very much. Have a great day. Have a great day, everybody. Hope to see you at the next webinar.
See you. Okay, bye.